In the previous video on electromagnetic induction, we saw through Faraday's law that whenever there is a change in flux around a circuit, there's going to be an EMF induced. Now you can see from these dot points that are highlighted here, we're going to take a step forward now and look at Lenz's law. And we're going to start off with the definition from the syllabus. And you'll see here that whenever we have an EMF, we're also going to have a current that will flow. So where Faraday's law deals with the EMF, Lenz's law deals with the direction of the current that subsequently flows as a result. Now the definition gives a little bit of insight into what's going on with the current flow in a loop when there is a change in magnetic flux around it. But there's a little bit more to it, so I'll write the definition first and then we'll have a look in a bit more detail at what that actually means. We'll go through a particular example and then we'll finish with a couple of other scenarios that will hopefully show you why it's important to make sure you have a good understanding of Lenz's law. So whenever the current flows, it's always going to oppose the change in the circuit or the change in the magnetic field around that circuit that produces the current. So that's the definition of Lenz's law, but let's try and unpack that and have a look at what that means in a bit more of a practical sense. And we're going to need to break it down into a few steps here. The first thing is that we need to identify that when a circuit experiences a change in magnetic flux. So that's the first thing to consider. Now note here I'm using the term magnetic flux. That change in magnetic flux can be caused a few different ways, and we'll talk about that later in the video. So the first thing, a change in magnetic flux is going to induce a current. So that means that an electrical current will flow around the circuit, and we always deal with conventional current, so keep that in mind as we talk about these concepts. The next thing to then consider is that that current will produce its own magnetic field. So anytime we have a current flowing, we know that a magnetic field will be produced around that current that forms concentric circles. And that means that we then have a magnetic field being produced by the current as well as a change in flux that produced the current in the first place. And this field that's produced will be in a direction that is opposite the change in magnetic flux that caused it. So note that we need to consider the change in magnetic flux, not just the direction of the external field. And be aware here that there are two fields that we're now dealing with. So we need to be very clear on the direction of the change in magnetic flux and the direction of the magnetic field that's produced around the current. So to do that, we're going to have a look at a specific example, and we'll include a diagram to make it a little bit clearer. And the diagram that we're going to deal with is very similar to the one that we saw in Faraday's law, where we had a uniform magnetic field, and in that field there is a conducting rail, and on that conducting rail there is a conductor that's free to slide along the rail. And as we saw, we'll have an induced EMF, and then we'll have a current that also flows. So there's the magnetic field, and the conducting rails positioned in that magnetic field with the conducting rod positioned over the top of it. And at some later point in time, that conducting rod is then going to be over further to the right. Again, I'll just indicate that by dashed lines. And we saw with Faraday's law that the top of the conductor is going to be positive and the bottom will be negative, with the positive charges being pushed up, negative charges being pushed down. That's ultimately going to mean that a current is going to flow in an anti-clockwise direction through that loop. Let's confirm that though with Lenz's law, so we'll step through that explanation of Lenz's law to make sure that we can arrive at the same conclusion. Now the first thing to do here is to consider that the reason the current flows is because of a change in the circuit, and that has to do with the area through which the field is passing. So if we indicate first of all that initially the area is given by this pink shaded area, let's call that area 1, and then at some later time that area has increased and is now given by this green shaded area instead. And we'll call that area 2. So the initial flux phi 1 is given by B multiplied by area 1, and the final flux phi 2 is given by B multiplied by area 2. And we can say that since the second area, area 2, is greater than area 1, then we know that the magnitude of phi 2 is going to be greater than the magnitude of phi 1. So the flux has increased. Now, to make a little bit more sense of this, we're going to consider it from a side view. So here we have the conducting rail with the conductor positioned on top of it, and then the conductor having moved to a new position at some later stage in time, and the field lines now will be directed downwards. So we're changing the orientation so we can look at the direction of the magnetic flux and identify how that has changed. Now keep in mind here that the downwards direction means into the screen, and the upwards direction really means out of the screen. And we'll come back to that when we have a look at the direction of the change in flux. Now, considering the initial flux, it's going to be down because it's in the same direction as the magnetic field, and it's going to be relatively small because that area is quite small. Whereas the final flux phi 2 is bigger, but still in that downwards direction. Note here that this diagram isn't necessarily to scale, but you can certainly see that phi 2 is bigger than phi 1. Now, if we consider the magnetic flux, we start off with phi 1 being relatively small and end up with phi 2 being greater. Now, to determine the direction of the change in flux, we can identify that delta phi is going to be equal to the final flux phi 2 minus the initial flux phi 1. Now, trying to do vector subtraction, not always the easiest, so instead we're going to change that and identify that phi 1 plus the change in flux will be equal to phi 2. That means that we can very easily identify here that the change in flux has to be downwards, so that we have that vector sum of phi 1 plus delta phi being equal to phi 2. Now the upshot of all of that is that we have the direction of the change in flux being into the screen, if we refer to the top diagram, as indicated also by the key on the left hand side. So the change in flux in this scenario is into the screen, and we know from Lenz's law that the magnetic field produced by the current will be in the opposite direction to that change in flux. So we can say that the magnetic field produced by the current is going to be in an upwards direction, which means that it's going out of the screen. So our magnetic field produced by the current here is going to be up, so out of the screen. So that means that we could represent it on the diagram above by using some blue dots to represent that magnetic field. And that magnetic field is produced by the current itself. Note that we're only considering what's happening inside the circuit. We're not worried about what's happening around the outside of the circuit. So let's summarize that in words to hopefully make a little bit more sense. So the first thing is that the change in flux due to the change in the circuit itself is into the screen. Secondly, the magnetic field produced by the current must be in the opposite direction to that. So given that the change in flux was into the screen, the magnetic field produced by the current will be out of the screen. Now that we have that direction, we can use the right-hand screw rule to identify the direction of current flow. So with the right-hand screw rule, hopefully you can recall that the fingers represent the direction of the magnetic field and the thumb represents the direction of the current. We can therefore identify that the direction of current flow will be anti-clockwise. So just to refer back to that diagram, you can see that with the field coming out of the screen, so arranging your fingers pointing out of the screen, imagine you're gripping that bottom rail so that your fingers are curling up underneath it. The current therefore will have to be directed in this direction through the rail at the bottom, and if you follow that around, you can therefore identify that it's going to the left in the top and coming down that rail on the left hand side, and so the current flow is in an anti-clockwise direction. Now you might be thinking, we've gone through all of that confusing explanation to identify the same direction of current that we did using Faraday's law, but unfortunately that's not always going to be the case. It's not always going to be as easy as that, because the change in magnetic flux, as I mentioned earlier, can be due to a number of different factors. The one that we've seen there is a change in the area of the loop itself, but there are two others that make it a little bit difficult to apply that same reasoning using Faraday's law. So the first, as we said, can be a change in area of the circuit or the loop that we're considering. The second is that the magnetic field strength itself can change. So we'll talk here about the strength of the magnetic flux density, otherwise known as magnetic field strength. So that means it could be a large magnetic field strength and then getting weaker, or vice versa. And finally, it could be a change in the direction of the magnetic field itself. Now I'm going to leave you with three scenarios here representing those three different options. I want to see if you can apply the understanding there to determine the direction of current flow in each of them. So in the first scenario, we're going to start with the magnetic field directed into the screen, and the loop that we're going to deal with is going to be circular in nature. Now, don't worry too much about the practicalities here of how this particular change comes about, but the loop itself will be circular and has a given area A1. And the final scenario is that the magnetic field hasn't changed, so the magnetic field strength is still the same and the direction of the field is still the same, but the area of the loop itself is going to have changed. So very similar to the example that we've just dealt with, but you can see now that the area is much greater. So there's the first problem to have a go at. The second one is going to have a constant area. So I'll draw both of those loops to begin with, and notice the loops are now square in nature. The shape doesn't really matter, it's going to stay the same. What is going to change is the strength of the field itself. So in this case, the field is now directed towards you or out of the screen, and initially looks like that. And then afterwards, so we'll call that B1, afterwards the field's going to be weaker, so we've now got fewer dots being represented here. So the spacing of the field lines are going to be wider, and therefore the field's going to be weaker. And so that's the second scenario where the strength of the magnetic field decreases. And finally, the third one to consider, again the area is going to remain the same, but the direction of the field is going to change. So initially the field is going to be directed out of the screen, and again we'll call that B1. And then afterwards the field is still the same magnitude, but it's now flipped around and it's now directed into the screen. So that will be B2. Now have a go at those, see if you can determine the direction of the current that would flow if you go through the same process as in the example above, and we'll have a look at those in class to help you understand how to arrive at the direction of current flow in those three scenarios. The last thing to consider with Lenz's law is how it ties into the conservation of energy. And two ways that we'll identify that is by first of all considering that the energy that's supplied in order to cause the change in magnetic flux is going to be converted to electrical energy. So the energy causing that change in magnetic flux, as I said, is thus converted to electrical energy. Or a better word there would be transformed. So we don't have any energy being created or destroyed. It's simply being transformed from usually kinetic energy into electrical energy. If we also consider a counter example, and that is to say if the current was opposite to Lenz's law, so instead of it opposing the change in flux that caused it, if the current flowed so that it enhanced the change in flux that caused it, the magnetic field produced by the current, as I said, would enhance that change in flux. And if that is enhanced, that means it's going to have an even greater change in flux. And if that change in flux is even greater, then you're going to have an even greater current. And if you've got an even greater current, you've got an even greater magnetic field produced by the current. And hopefully you can see we're in a bit of a cycle here that we're going to see an even bigger and bigger change in magnetic flux leading to an even bigger and bigger current. And hopefully you can see there that we would have more energy being produced than was initially input into the system. And that violates the conservation of energy, in that we can't have more energy being produced. Energy is neither created nor destroyed, it's only transferred or transformed. So hopefully those two explanations help to make sense of how Lenz's law is consistent with conservation of energy.